There is a river of light that flows across the darkness of the sky. You've seen it on clear nights, away from the glow of cities, a pale band stretching overhead like a cosmic highway. The ancient Greeks thought it was spilled milk. The Norse imagined it as a path to the afterlife. We call it the Milky Way galaxy, our home. And here is the paradox. The Milky Way is simultaneously one of the largest structures in the universe and almost nothing at all. Both statements are true. Both are verifiable. And understanding how they coexist will change the way you see that band of light forever. Let's begin with what we can measure. The Milky Way stretches roughly 100,000 light years from edge to edge. A distance so vast that light itself, racing at 300,000 kilometers per second, requires 100,000 years to cross it. Tucked within this spiral galaxy are somewhere between 100 billion and 400 billion stars. Our Sun occupies an unremarkable position about 26,000 light years from the galactic center, nested in a minor spiral arm called the Orion Spur. Not at the center of anything, just here in the suburbs of the galaxy, where stars are not densely packed and supernovae are rare enough that complex chemistry could unfold over billions of years without interruption. Every star visible to your naked eye belongs to this structure. Every constellation humanity has named, every shooting star witnessed, every planet glimpsed in twilight, all of it part of this one cosmic edifice. Here's where the numbers become interesting. When astronomers survey the universe, cataloging galaxies across cosmic distances, they find that approximately 95% of all galaxies are smaller than the Milky Way. Most are dwarf galaxies, small collections of a few billion stars, sometimes less, faint, unremarkable, common as sand. The Milky Way, by contrast, sits comfortably in the top 5% by size, not the largest, but genuinely large, a giant among galaxies. And yet, the Milky Way does not exist in isolation. 2.5 million light years away, Andromeda glows in the darkness, containing roughly 1 trillion stars, more than twice our number. Then there are the Magellanic Clouds, 2 smaller satellite galaxies orbiting the Milky Way, visible from the southern hemisphere. The large Magellanic Cloud contains perhaps 10 billion stars. The small Magellanic Cloud, a few billion. These galaxies, along with about 50 others, form what astronomers call the local group, our cosmic neighborhood. Most members are dwarf galaxies. The Milky Way and Andromeda dominate like 2 large siblings surrounded by dozens of smaller ones. The local group spans roughly 10 million light years across. That sounds massive. It is massive. But the local group is merely one tiny cluster in a much larger structure called the Virgo supercluster. The Virgo supercluster contains at least 100 galaxy clusters and groups. Its namesake, the Virgo cluster, sits about 54 million light years distant and contains somewhere around 1,000 to 2,000 galaxies. Some dwarf the Milky Way entirely. The Virgo supercluster as a whole contains roughly 100 trillion stars spread across 110 million light years. The Milky Way seemed large at 100,000 light years across. The Virgo supercluster is 1,100 times wider. Our entire galaxy, with all its hundreds of billions of stars, is a tiny speck. If the Virgo supercluster were a city, the Milky Way would be smaller than a single room in a single house. And we're still not seeing the full picture. In 2014, astronomers discovered something even larger. The Virgo supercluster itself is just a small component of a vastly more massive structure called Laniakea. The name derives from Hawaiian, meaning immeasurable heaven, fitting because Laniakea is almost incomprehensibly large. Laniakea contains approximately 100,000 galaxies spread across 520 million light years. All of these galaxies, including ours, are slowly moving toward the center of Laniakea, drawn by the combined gravity of the immense concentration. The Milky Way isn't sitting still. We're falling, along with everything else in Laniakea, toward a region astronomers call the Great Attractor. If you could shrink Laniakea so that the Milky Way became the size of a grain of sand, the entire structure would be about as large as a room. We've gone from thinking our galaxy encompasses everything to realizing it's less than a speck of dust. But we're still not finished. Laniakea is enormous, but it's just one supercluster among many. Zoom out further, and the universe reveals itself as a cosmic web, filaments of galaxies stretching across billions of light years, connected by threads, separated by enormous voids where almost nothing exists. The observable universe extends roughly 93 billion light years in diameter. Why 93 billion when the universe is only 13.8 billion years old? Because space itself has been expanding. Light from distant galaxies has traveled toward us for billions of years. But during that journey, space has stretched, carrying those galaxies even farther away. Within this observable universe, astronomers estimate there are approximately 2 trillion galaxies. The Milky Way is one of them, not a special one, just one among 2 trillion others. If we represented every galaxy as a single grain of sand, we would need several Olympic-sized swimming pools to contain them all. The Milky Way would be one grain in that vast collection, indistinguishable from the rest. Now let's examine some of these galaxies, because understanding the full range helps us grasp where the Milky Way truly sits. Consider IC 1101, one of the largest galaxies ever discovered. It stretches approximately 6 million light years across, 60 times wider than the Milky Way. This single galaxy contains roughly 100 trillion stars, about 250 times more than we have. It's so massive that if you replace the Milky Way with IC 1101, Andromeda would actually be inside its boundaries. But IC 1101 is not normal. It's exceptional. Out of trillions of galaxies, only a tiny fraction are this large. Then there's M87, a supergiant elliptical in the Virgo cluster, roughly 120,000 light-years across, slightly larger than the Milky Way, but containing around 1 trillion stars compared to our few hundred billion. M87's central black hole has a mass of about 6.5 billion times the mass of our Sun. The black hole at the center of the Milky Way is only about 4 million solar masses. M87's black hole is more than 1,600 times more massive. These giants are impressive, but here's the critical point. They are extremely rare. For every IC 1101 or M87, there are thousands upon thousands of galaxies smaller than the Milky Way. The most common galaxies in the universe are dwarfs, small collections containing a few million to a few billion stars, typically just a few thousand light-years across. They're everywhere. This pattern repeats across the cosmos. Every large galaxy is surrounded by dozens or hundreds of smaller satellites. Our local group contains about 50 known galaxies. The Milky Way and Andromeda are the 2 giants, then Triangulum, and then dozens of tiny dwarfs. When we compare the Milky Way to the average galaxy, to the typical galaxy you'd encounter if you randomly selected one from the universe, the Milky Way is huge. The typical galaxy is a dwarf containing maybe 1 billion stars, spanning a few thousand light-years. The Milky Way, with its hundreds of billions of stars and 100,000 light-year span, is exceptional. Imagine gathering 1,000 random galaxies. Probably 950 would be smaller than the Milky Way. Maybe 40 would be roughly similar. Perhaps 10 would be larger, with only 1 or 2 dramatically larger. The Milky Way isn't in the top 1%, but it's comfortably in the top 5%. That makes it large, genuinely large by cosmic standards. Between the superclusters lie the voids, vast empty regions just as important for understanding scale. The largest known void is the KBC void, roughly 2 billion light-years across. Inside it, there are very few galaxies. Our Milky Way could fit across the width of the KBC void 20,000 times. Even Laniakea, that immense supercluster containing 100,000 galaxies, would fit across the void less than 4 times. These voids make up about 80% of the universe's volume. Most of space is empty. The universe is like a vast ocean with islands of matter scattered throughout. And the Milky Way is a single grain of sand on one of those islands. Then there are the cosmic walls, structures so large they challenged our understanding of how the universe could have evolved. The Sloan Great Wall, discovered in 2003, stretches about 1.37 billion light-years across, containing tens of thousands of galaxies. If the Milky Way were the size of a grain of rice, the Sloan Great Wall would be longer than 10 football fields placed end to end. And then there's the Hercules Corona Borealis Great Wall, the largest known structure in the universe. Stretching across approximately 10 billion light-years, the Milky Way is 100,000 light-years across. This structure is 100,000 times larger. If you traveled at the speed of light, it would take you 10 billion years to cross it, more than 70% of the age of the universe itself. This structure contains billions of galaxies, and yet even this enormous structure is just one part of the universe's cosmic web. These structures didn't form randomly. In the very early universe, tiny density fluctuations existed. Some regions were slightly denser than average, others slightly less dense. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter. Less dense regions lost matter, becoming voids. The result is the cosmic web we observe today. But this web isn't just made of visible matter, stars, and gas. It's primarily made of dark matter. Dark matter forms the scaffolding. Visible matter falls into this scaffolding, collecting in the densest regions where it can form galaxies and stars. When we talk about structures like the Sloan Great Wall, we're really talking about concentrations of dark matter that happen to contain tens of thousands of galaxies. The galaxies are just the visible parts. Like lights on a Christmas tree, the tree itself, the structure holding everything together, is made of dark matter. The Milky Way sits in this cosmic web, held by dark matter, connected to other galaxies through filaments of dark matter. We are part of something much larger than ourselves, and that something is incomprehensibly vast. Now we arrive at the heart of the paradox. How can the Milky Way be both enormous and tiny simultaneously? The answer lies in perspective. Scale is relative. It depends entirely on what you're comparing. When we compare the Milky Way to most galaxies, to the dwarf galaxies that constitute 95% of all galaxies in the cosmos, the Milky Way is enormous, a giant containing hundreds of billions of stars. Most galaxies will never be this large. The Milky Way is exceptional, in the top 5% by size. But when we compare the Milky Way to the largest galaxies, to supergiant ellipticals like IC 1101 or M87, it's smaller. Those monsters contain trillions of stars and span millions of light years. They dwarf the Milky Way. And when we zoom out further to look at superclusters, cosmic filaments, and the observable universe itself, the Milky Way becomes just one galaxy among 2 trillion. A large galaxy, yes, but still just one piece in a structure so vast it defies comprehension. Both things are true simultaneously. The Milky Way is large, genuinely, impressively large, but the universe is so vast that even a large galaxy becomes insignificant when you zoom out far enough. It's like being a tall person in a crowd. You might be taller than 95% of people around you. That makes you tall, but stand next to a skyscraper and suddenly your height seems irrelevant. Both can be true. You can be tall and also tiny, depending on what you're comparing yourself to. Within this observable universe of 2 trillion galaxies, astronomers estimate there are about 200 billion trillion stars. Many have planets. The Kepler Space Telescope showed us that planets are common. Most stars have at least one planet. If even a tiny fraction of these planets can support life, the numbers become staggering. If just 1 in every million planets can support life, there's still 200 trillion potential homes. And if intelligent life arises on just 1 in every million of those, that's still 200 billion civilizations. Yet we've never detected a signal from any of them. The galaxy seems silent. This is the Fermi paradox. Where is everybody? Maybe life is rarer than we think. Maybe intelligent civilizations destroy themselves. Maybe they're staying quiet. Or maybe space is just too big. The Milky Way is 100,000 light years across. A signal from the other side would take 100,000 years to reach us. by the time it arrived, the civilization that sent it might be long gone. The scale isn't just humbling, it's isolating. The observable universe, 93 billion light years across, is just what we can see. The actual universe is almost certainly much larger. It might even be infinite. We have no way of knowing because we can't see beyond the observable limit. If the universe is infinite, then the observable universe, vast as it is essentially nothing. 0% of infinity is still 0. And in an infinite universe, the Milky Way isn't just small, it's infinitesimally small, less than a grain of sand on a beach, so small that adequate comparisons fail. Some theories suggest our universe might be just one of many in a multiverse. According to eternal inflation, the Big Bang wasn't a single event, but is happening constantly, creating bubble universes that spawn more bubbles. Our universe would be just one bubble in an infinite foam. If the multiverse exists, then our universe, already unimaginably large, is just one of many, and the Milky Way becomes even more insignificant. This is a humbling realization, but it's also liberating. For most of human history, we thought we were the center of everything. Then we learned Earth orbits the Sun. Then the Sun is one star among many. Then those stars form a galaxy. Then our galaxy is one among many. Then those galaxies form superclusters. At each step, we've been knocked down a peg. We're not central. We're not special. We're not even particularly large. But that doesn't make us worthless. If anything, it makes us more valuable. Because in all this vastness, as far as we know, Earth is the only place where life exists. We might not be alone, but we're certainly rare. And conscious, intelligent life, capable of understanding all this, that might be rarer still. You are made of atoms forged in stars that died billions of years ago. Those atoms drifted through space, eventually forming Earth. And then you're a way for the universe to know itself. Out of countless planets, in all the galaxies across all of space, you're here, able to think about these questions. The Milky Way might be small compared to the universe, but it's your home. Every star you can see belongs to it. Every constellation, every myth humans have told about the night sky for thousands of years, all of it comes from this spiral. So when you look up at that band of light stretching across the night sky, remember, you're looking at home. Home is large. The cosmos is larger. and both truths make our place in the universe all the more remarkable.